Hello and welcome to this lecture series on microprocessor and microcontroller, and we are reading the concepts of interfacing as of now, right? So in the previous lecture we have dealt with interfacing of memory to 8086. And we said that if we could understand it for 8086, it will be also understood for 8085, right? Because 8086, because of its memory organization in odd and even banks, it requires little more attention. Now, in this video lecture for 8085 as well as for 8086, we are going to study something which is known as 8255 PPI. PPI means Programmable Peripheral Interface, right? So, Programmable Peripheral Interface, a close match to that in today's terminology or in today's world is a USB hub, right? So, USB hub is just one example where through various USB ports, you can connect various input output devices. It may be mouse, it may be keyboard, it may be something else that you want to connect to your computer, right? So in those days, we had 8255 programmable peripheral interface. The first thing is it is programmable, right? The second thing is it is peripheral interface. Peripheral interface because you can interface various devices by using that interface. And it is programmable. That is of advantageous nature for us. Why? Because 8085 or 8086, that means in general we do not want our microprocessor to be busy with these peripherals. We do not want it to be interrupted a lot of times. We do not want it to check the status of peripherals, uh, whether it is ready for transfer, whether it is not ready for transfer, so on and so forth. So this task has been given to this special IC, which is called as 8255 programmable peripheral interface. And since it is programmable, so it will reduce the burden of this microprocessor, either 8085 or 8086, right? So that's what we are going to study today. That's what we are going to study today in this particular lecture. And before beginning this lecture, let us also understand that in your computer, if you are using an older computer, then you might have got some ports at the back of your CPU where you had special ports for mouse and for keyboard, right? They were only input ports and they were only made for mouse. Nowadays you can just interface your mouse by using USB also, but in some older computers there were dedicated ports for putting the connection of mouse, and you did not have USB mouse. We had special mouse. I mean, the mouse will look exactly same as what we have now, but the connection was not made to USB. It was made to a special interface which was only for mouse. So there were some dedicated input ports. So it's not that the CPU always has a port which can function as input and output for port always. It can function as input only or as output only, right? So depending upon that, we have various modes of operation, right? So some ports are only input ports, some ports are output ports, and some ports are bidirectional in nature, right? Some ports are like, if you use them as input port for once, then you have to use them as input for port for rest of the life of that computer, right? It then cannot be converted into an output port. So this is also some kind of rigid nature that some ports possess in some older computers, right? So those all things will be seen here. Those all things will be seen here. So let me just begin. Let me just begin. Let me just see my slides. Okay, I have slides in this BMP format only. Yeah. So let's begin by seeing the pin diagram of 8255 programmable peripheral interface, right? You're not supposed to remember this pin diagram, but this pin diagram should make sense to you. That's what we should focus on here, because 8085 and 8086, their individual pin diagrams are already very huge. And 8255 programmable peripheral interface, it is also IC, which you can see it has got 40 pins again, and you're not supposed to remember all the positions of the pins, etc., but this should make us sense logically, right? So first of all, this device 8255 is like onion, right? It has multiple layers to understand. So pay special attention to this lecture because it has got multiple things which you need to understand to be able to take the advantage of this device to help you interface some input output devices, right? Okay, so let me begin by just showing you this pin diagram. In this pin diagram, you can see that from this 8255 IC, first of all, it has got three ports: port A, port B, and port C, right? And this port A, it is of 8 bits, port B is of 8 bits again, and port C, it is again of 8 bits, right? But port C can be broken into two nibbles. It cannot be, I mean, it can be used as a single byte, or it can also be used as two 4-bit ports, right? So port C can be broken into two parts. So port A, port B, port C. Port A is 8 bits, port B is 8 bits, and port C is also 8 bits, but it can be used as two separate ports, which is called as C upper and C lower, right? And since this device is programmable, so we also have some control register inside it, and that control register has some format according to which this complete IC will function, right? So then, this port A and the upper part of port C, when they are combined, they can be used combinedly, but I mean, not to transfer the data of 8 plus 4, that means 12 bits, but when they are grouped together, they are called as group A. So port A and the upper part of port C can be grouped together, and that is called as group A. So you should understand the difference between these two terminologies, a port and a group. When I say port A, it simply means port A of 8 bits. But when I say group A, it means port A and upper portion or upper nibble of port C. Similarly, this port B plus the lower nibble of port C, that is the lower 4 bits of port C, when they are combined, it is called as group B. So you can say it in this way, that you have three ports, right? Or you can say you have two ports of 8 bits and two ports of 4 bits each. Or you can say you have two groups. Two groups means one group will have port A and the upper part of this port C, and second group, that is group B, will have port B plus the lower part of port C. So that is how you can interface your devices. So some older devices which had only 4-bit connections, they can be used with upper or lower part of port C, right? So it's not that if you have formed groups, then that means you can take 12-bit data also combinedly. That's not what I am saying. I am just saying that they are grouped. And what is the advantage of that group? We are going to see it soon. Now, since this device is programmable, 8255 is programmable, that is why we have got a control register also, right? Now, let us have a look at the structure of this IC. So, here you will be able to say the 8 bits of port A, that is PA0, 1, 2, 3, and then this is 4, 5, 6, 7. So, these are the 8 bits of port A. Let us see the bits of port B also. So, PB0, PB1, PB2, and this is 3, 4, 5, 6, and 7. Yeah. And then for port C, you can see it here. It starts from PC0, PC1, PC2, PC3, and then 4, 5, 6, 7 here. So they are not ordered in this numeric order. They are just ordered in some random fashion which suited the construction of this particular IC, right? Now, these are two special pins, A1 to A0. These A1 and A0 pins, these are the address pins of this particular IC, and they're only input pins. What is the usage of them? See, this 8255 IC, it has got these ports, right? Which port are you using at one particular time? It will be decided by this A1 and A0 bits combination. So if it is 00, you are using port A, 01 port B, 10 port C, and 11 you are trying to modify the control register, right? So if the control register is modified, this IC can perform in various different ways. That's what we are also going to see. Now, apart from these ports, you have got a ground signal, which is obviously there for any IC. And after that, you have got this chip select signal. So chip select signal is an important signal because 8255 is not activated most of the times. Whenever this microprocessor feels like it wants to address the peripherals, then for that purposes, we have this chip select signal. That is why only this is an input signal. Now, read signal, you will also see it's an input signal. If the microprocessor 8085 or 8086 wants to read something through this IC, then it will give this read signal as logic one, as logic 0 value, because this is read bar, so it will be activated when it is at logic 0. So only in that case this peripheral device will be selecting an appropriate port depending upon A0 and A1, and it will be reading the data from that particular port, right? So this read signal, it comes from microprocessor. And after that, there is also this write signal. As you can see, this write signal also comes from this your externally interfaced peripheral, so that if that peripheral wants to write something to the microprocessor, then it will go through this 8255 PPI. So that's why this write signal is being used here, right? Apart from that, you see this reset signal. This reset signal is actually connected to the reset of microprocessor. So whenever you will reset the microprocessor, this 8255 will also be reset. And what does it mean to reset 8255 IC? All it means is the control register, which we are going to see soon, there is a format for that. There is a 8-bit format for control register. All of the bits of that will be reset, right? All of them will become 0. And this 8255, every port that you see here, A, B, and C, it will by default come in input mode. So it will by default come in input mode. This port A and this port B and this port C, they all will come in input mode whenever this reset signal is received as high. So microprocessor will also be reset together with this 8285 will also be reset. And resetting means all the ports will be kept in input mode, and control register, it will be reset. Every bit of that will become 0, right? Then you have got this bidirectional data line. So you can see this D0 to D7. So this is 8-bit data bus can be connected to this. Now you will say that how will you be able to connect your 8086 data bus, because 8086 is a 16-bit microprocessor. So when we saw the instruction set, we saw that there are commands for transferring 8-bit data also, right? Because you can use 8-bit register and you can transfer 8-bit data into that. So an example could be move, and you can use AH, and then you can transfer a 8-bit data. So 55H. So those commands were there. So half of the portion of the data bus of 8086 can be used and can be connected here for dealing with the 8255 programmable peripheral interface, right? Apart from that, there is this VCC pin. So this VCC pin will obviously be there for putting this voltage, which is very basic for any IC. So now, so this is all about the pin diagram. So we have understood that there are ports and there are control registers. So control registers will it will select the operating mode of 8285, right? So here the summary is also given. This P0 to PA7, it is called as port A pins. They are bidirectional in nature. Similarly, port B, port C, and this PD is not port D. It is actually data bus, right? So we have got this data bus here. Then reset, it only acts as input. Then you have got read bar signal. So its direction is only input. This is not one, this is input, right? Similarly, this A0 to A1 and write signal, they are also input signals. Chip select and VCC and ground, they are also input signals, right? It needs a plus 5-volt ground supply, right? So this is about the pin diagram and a general description of 8255 programmable peripheral interface. Now let's have a look at the functional pin diagram or the functional diagram of 8255. So on the right hand, you can see the functional diagram of 8255 programmable peripheral interface, right? So you can see that there is this group A. Group A means there will be this port A, and the group A is also there. So port C's upper 4 bits are also there. So this is your group A. So port A is of 8 bits, and this upper portion of port C is there. So these two combined, they form group A. And to be able to control group A, we have got group A control here, right? And this is the internal data bus of 8255 system, which is also connected to the external microprocessor, whatever microprocessor is used. Similarly, you have got group B, in which you have got port C's lower 4 bits, and you have got port B, 8 bits of that. I mean, full port B is there, right? So these are the interfaces onto which you will be attaching your externally interfaced peripherals, right? In the previous lecture, we saw that in memory mapped input output, you can attach as many peripherals as you want to your computer, depending upon the width of the data bus. So for 8086 microprocessor, it was 2 raised to the power of 16. But it seldom happens that we put that many peripherals into our computer, right? So um, We usually use only keyboard and mouse and maybe one or two USBs and some devices to listen to music, I mean speakers, etc., sometimes mic also. So in today's scenario we hardly use maybe 5 to 10 devices to connect to our computer system. So in those days they were still fewer, so they gave you a facility of these three ports: this complete C port, this is port A, and this is port B. So you can connect it through that, right? Then there is this data bus buffer. This data bus buffer is necessary because the externally interfaced data bus from the microprocessor is connected here, and this buffer is there. So the data will be read into this, right? And then you can see this read write control logic. So all of these pins that you see here, read, write, reset, and chip select, they all come from microprocessor A0 and A1. So this A0 and A1 is the actual A0 and A1 of any microprocessor that you are using, whether it is 8085, 8086, or otherwise, right? So this is a functional pin diagram, and on the left hand side you can see how a 8255 PPI, that is programmable peripheral interface, is connected to a microprocessor. So here we have used a 8085 microprocessor, and to be able to generate the chip select signals, we have used a NAND gate, and here this A2 and A7 have been attached, and this is used to generate the chip select signal, right? Then you can also see this 8085 microprocessor, it has input output slash memory bar pin, it has write bar pin and read bar pin. We have read about this a lot, and these are given to a suitable decoder, and that decoder will generate your input output read signal and write signal, etc., and it will supply it to 8255 PPI. Then this reset signal is connected to the reset of 8255 PPI. So this is fairly simple. We need to pay some special attention here. You can see that um, if you see this 8085 microprocessor, its data bus is only of 8 bits, right? 8 bits wide data bus, 1 byte data bus is there since it's a 8-bit microprocessor. So this data bus, it is connected to the data bus of the 8255 PPI, right? And there is a latch, but the purpose of this latch is not to latch the data of the data bus. It will only take this A0 and A1. This A0 and A1 will be taken and they will be latched in this, and they will be supplied to this 8255 PPI. So the purpose of this latch is not to latch the complete data bus. Here we are only interested in A0 and A1 bit of address lines. And why we are interested in this? Because we saw that A0 and A1 will help you select some port, or they will help you select the control register, right? So that's why this latch is different as the latch that we have used, which is used for taking the complete 8-bit data, but this latch is only taking the data of 2 bits, A0 to A1, right? And you can see that this peripheral is already there. We have talked a lot about this peripheral already. Now let us come to the modes in under which this complete 8255 operates. So 8255 operates in two modes. The first mode is called as bit set reset mode, BSR. This BSR mode is there, and this BSR mode is only applicable to port C. BSR mode is only applicable to port C. So we will talk about it in a while. And another mode is input output mode of 8255 programmable peripheral interface. So this IO mode of 8255 PPI, it is available to all kinds of ports. So group A ports, that means port A, port B, and port C, every port can be used here. But this input output modes of 8255 PPI, they have got further classification. So we will come to that. But let us first discuss bit set reset mode, which is called as BSR mode for short, right? Now, what is the purpose of this bit set reset mode? First of all, it is used only with port C, right? And if you see here, this is the control word register, the register that I was talking about in this slide. This control register's format for bit select set reset mode is given here, right? So this control word register, it will be the same for BSR mode or for IO mode, right? But for BSR mode, its format will be different, and for IO mode, its format will be different. And whether it is in BSR mode or IO mode, it is decided by this most significant bit of the control bus, right? Don't be confused with this notation of D0, D1, etc. This is not the data bus. This is the format of control word register, CWR for short. So CWR is specific to 8255 programmable peripheral interface. Now, if the most significant bit is 0, then we are working in BSR mode. If the most significant bit is 1, then we are working in the IO mode, right? So as of now, the most significant is bit is 0. So we are working in BSR mode, and the format applicable to BSR mode is this. These three are don't care, and then you have got the last four bits which are useful. So if you see this D1, D2, and D3, this corresponds to B1, B2, and B3, right? And what is this B1, B2, B3? Whatever data is there according to this table, bit number 0, bit number 1, bit number 2 till bit number 7 of port C will be selected, right? Because port C is a 8-bit port, although it can be divided into two nibbles, but it's completely a 8-bit port. And in this bit set reset mode, what we are trying to do is we are trying to select one bit of that port, and we are trying to set or reset it. So how do we select that bit? You just put the format here, B1, B2, and B3. So B1, B2, and B3 are here. Whatever number you will put here, that particular bit will be selected. After selecting that bit, do you want to set it or reset it? So if you want to set it, you have to put a 1 in the least significant bit of this control um, word register. So if you want to set it, put a 1 here. If you want to reset it, you have to put a 0 here. So whatever data is there, it will be directly copied to that location in port C. So this is as simple as that, right? So this is as simple as that. So BSR mode is very simple. It is applicable to port C, and in port C, you can set or reset any bit as you want. Now, this is the general format of control word. This format that we have just discussed, it is applicable only for this bit set reset mode. But this is the general format of control word, and this D7, it decides whether we are operating in BSR mode or we are operating in IO mode, right? So BSR mode, bit set reset mode for port C. So for port C, it is applicable and no effect on IO mode. So if the control word register is initialized with BSR mode, then it will have no effect on IO mode, right? Then after that, if it is in IO mode, if it is in IO mode, then this bit will be 1, and IO mode further has three bifurcations: mode 0, mode 1, and mode 2. Now, before discussing the technical details of this mode 0, mode 1, and mode 2, let me just tell you that mode 0 is little bit unreliable, and mode 1 and mode 2, they are reliable. What do I mean by reliability here? Suppose you want to transfer some data to some other person, right? And that person is slower as compared to you, right? So if you keep on just sending him uh, maybe say some packets of something, then that person is slow at collecting those packets, right? So if you send packets, suppose 100 packets in 1 minute, then that person might be able to take 50 packets only. So in that case, there is a loss of the data. There can be a loss of data, right? So you have to take care. You have to take care that you should work at his speed. So it will be your headache. So mode 0 is something which is like that, right? So here the microprocessor will have to take care, not the 8255 PPI. Microprocessor will have to check the status of this externally interfaced peripheral, but the data will be transferred through the 8255 PPI. So this mode 0 is there and is applicable for A, B, and C, all the ports, where all the ports can be programmed as either input or output port in any combination, right? So mode 1 and mode 2, they are reliable. In mode 1 and mode 2, what happens is whether the peripheral is slower as compared to us or whether it is not slower as compared to us, what we will do is we will first of all send some data, and until that person acknowledges, we won't send next data. So mode 1 and mode 2 are like that, right? But the difference between mode 1 and mode 2 is this, that in mode 1, if you have decided that you will be sending and the person will be receiving, so this will continue throughout. Then you cannot change it the reverse phase. If you are the sender and that person is the receiver, then that person will always be on receiving side. He cannot reverse the situation and send some data to you. However, in mode 2, both possibilities are there. I mean, this reliability is already there, but in mode 2, you can send the data to the person or the person can send the data to you. Right here, U means 8255 PPI. And in this mode 1 and mode 2, there is a special facility of making this transfer through handshaking. What do I mean by handshaking? Handshaking technically means when you send some data to someone, they receive it, and after receiving they acknowledge it, so you know that the data has been correctly transferred. After that process is over, you will be sending the next data, right? So this process of acknowledgement etc will be there in mode 1 and mode 2. So mode 1 is unidirectional, however mode 2 is bidirectional, right? So this mode 1, let's come to the technical details. Mode 1, it is handshaking, input output will be there, and for handshaking purposes we will always use port C, right? So handshake input output mode for port A or B, so A and B ports will be used here, but port C are used solely for handshaking here. So port C won't be able to transfer data as a whole. Port C will be involved in the process of handshaking, means establishing reliability between port A, port B, and the externally interfaced peripheral, so that acknowledgement process etc will be achieved through this port C. Similarly, in this mode 2, but it is bidirectional in nature, handshaking process will also be there. uh, Data bus for port A and I mean, this mode 2 is only applicable to port A. Port A can perform in mode 2, but port B will not be able to perform in mode 2. Port B can be programmed in either mode 0 or mode 1. Mode 2 is not applicable to port B, right? And after that, port C, as we already know, it will be engaged in this process of handshaking, right? So with this general introduction to these modes, now let us discuss the IO mode in great details, right? So as I told you that this 8255 is a simple IC, but it is like onion. There are many layers under which it works. We have understood one mode, which is called as bit set reset mode, which is applicable to port C. Now we are going to understand this IO mode. In this IO mode, that is input output mode, three modes are possible: mode 0, mode 1, and mode 2. And we have already seen to which ports are they applicable and what are their roles. Now let us further elaborate on the IO modes of 8255 PPI, right? So this is the control word register format for IO mode, and here you can see that the most significant bit is 1, the control word register, which is controlling the entire 8255 PPI IC. Because of this control register, this 8255 is PPI, right? That is programmable. So this control word register, microprocessor can override this control word register according to his wish, right? But it cannot I mean, microprocessor can just control this control word register. So this microprocessor will be sending the information to this, and this control word register will be modified accordingly, and accordingly this 8255 PPI IC will perform, right? So here you see, if this most significant bit is 1, then D5 and D6, they are applicable to group A. By group A I mean port A plus upper bits of port C. So mode is applicable, this D6 and D5. So this mode is applicable for group A, and as we know that group A, it can operate in mode 0, mode 1, or mode 2. So port A can operate in mode 0, mode 1, and mode 2, and port C in mode 0 and mode 1. So for this group A, this mode selection is done by this. So you have this 2 bits, and the meaning is also written here. So this X is don't care, so it can be either 1 1 or 1 0 for mode 2, right? After that, in group A we have two things. One is port A plus upper 4 bits or upper nibble of port C. So this for individually port A, what it will be doing? Will it be acting as an input port or an output port? So this bit will tell you that if this is 1, it is the input port, or otherwise it is the output port. And what will individually this C port do? Will it be a input bit or a output bit? So it will be told to you by this. So up till from this D3 to D6, everything is for group A. So first of all, the mode will be decided for group A by these two bits, and what these two individual components of this group A, that is port A and your upper nibble of port C, they will act as input or output. So it will be decided by this particular thing, right? After that, the same thing is there for this group B. But as I told you that inside group B, there are two things, port B plus the lower nibble of port C. So in that case, group B, as we have discussed, it cannot operate in mode 2. It can only operate in either mode 0 or mode 1. So we only need one bit for selecting the mode. And here the case was opposite because it can operate in three modes. So in binary, you will need at least two bits to address numbers up to 4. If there are total 4 numbers, then 3 can not be accommodated in one bit. So for this group B, the mode selection is done by this D2. And if you see this, what will port B do? Whether it acts as input port or output port, so it is done by this. And for port C, you have this last bit, right? So this is the format of control word register for 8255 programmable peripheral interface. Now, after this, let's come to mode 0. It's very simple mode where you have a microprocessor, a 8255 programmable peripheral interface, and with that 8255 programmable peripheral interface, you have got various devices which can be attached. So let us first read what are the features of mode 0. First is two 8-bit ports PA and PB and two 4-bit ports PCL, that is C lower and C upper, are available. So we know this, right? Then all the ports can be separately programmed as input or output. How will we program them? We already know this format, and according to this chart, we can just select the numbers that we need to fill in this control word register, and accordingly that will be programmed, right? After that, if the port is programmed as output ports, the outputs are latched, right? So if some port of 8255 it is acting as output port, then obviously there will be some latching mechanism because we need the output to be there so that the peripheral can read that. If the port is programmed as input port, the inputs are buffered, right? Because if microprocessor is trying to send some data, or this peripheral is trying to send some data to this 8255 PPI, in that case the data should be buffered somewhere so that when the 8255 PPI is ready, it will be keeping it in itself. Then, as 4 ports are to be used, 16 different I/O configurations are possible, which is very natural because we have PA, PB, PCL, PCU. So any combination of them can be used. And no facility for interrupt-driven input-output is present. So we will elaborate more on this point. This point will become more clear to you when we will discuss mode number 1 and mode number 2, because there this handshaking process will be achieved through this interrupt, right? So obviously in mode number 0, we do not have any facility for handshaking. So this interrupt is obviously not there. No facility for interrupt driven IO is there. And now this is the timing diagram. Here, one special point to note is that in 8255 programmable peripheral interface, uh, you actually do not see any T1, T2, T3, T4 cycles. Why? Because 8255, it does not have its own clock. It does not have a clock. No clock input is there in the IC diagram also. Let me just take you to the IC diagram again. So you will not find any clock signal here. You will not find any clock input here. So this is not something which is synchronized to the microprocessor. So in the timing diagram of this, there will be no T states. So then one fundamental question is, how do we call it as a timing diagram? So the answer to this is, although it does not have a sequence of clock cycles, but the signals that are initiated, they are initiated in certain order, one signal after the other, and after that this could be done, and after that that could be done. So that sequence should be retained. So that's what we call as timing diagram. So an interesting point to note here is that in 8255 PPI, the timing diagram does not have time, right? And still we call it as a timing diagram. So when we are operating in mode 0, so suppose we are trying to read something. There is a peripheral which is connected to 8255 PPI. We want that peripheral to be and we want that peripheral to give us some data, because the 8085 or 8086 microprocessor, which is the main microprocessor of the system, it is telling us to read that peripheral through 8255 PPI. So, what will be the sequence of operations? First of all, this chip select signal has to be activated, and A0 A1 will decide which port is to be selected. So you can see that this cross appears here, mean the status of the signals will change first. So in this box, you can see for this particular duration, the CS will be 0. I mean, CS bar is 0, so CS is activated. That means the 8255 PPI will be selected. Then A0 and A1 will be given appropriate values. So here they have given 0 0 value, so port A is selected, right? So after this has been initialized, what will happen is, since you have selected port A, after selecting the port A, then definitely the peripheral can put the input data. So you can see that after this timing, at this particular timing, the peripheral has inputted some data here. And once the data it comes to 8255, once the data it comes to 8255 ports, this microprocessor will enable its read signal, right? So read signal will be enabled, and you can see that in this particular duration, the data will be transferred from your 8255 to microprocessor. So in that case, the data will come from the externally interface peripheral to 8255 and to the microprocessor. So this happens in this particular duration. So this is as simple as this, right? We only need to remember this sequence of signals which need to be operated. Even if you don't remember this diagram, you can think logically without looking at this diagram, that suppose you are the microprocessor and you want to take some data from the peripheral which is connected to 8255. What will you do first? You will activate 8255 IC first. So for that, you need to have this chip select signal. After activating it, what do we need? After activating it, we need to tell it that you should use this port because I want to read the data from port A. So these signals have to be initialized first. After that has been done, your peripheral can put the data onto 8255. So that's what happens here. And after that, the microprocessor can lower this read signal line. That means this read bar signal is line is lowered. So this is activated because this is active low signal. And then the process of reading happens. So this is as simple as that. So mode 0 is very simple mode. But as I told you that it's very unreliable because if the microprocessor is not as slow as the peripheral that is interfaced, then there can be some data loss. Now, on that note, we come to this mode 1, which is called as strobed input output mode, right? This is strobed input output mode is there. So first of all, we are discussing only input. In this portion, we are discussing input, and in this portion, we will discuss the output part of that. Now, uh, so let me first just show you what is this handshaking process and how things happen. So as I told you that in mode 1, there is a facility of interrupt driven input output. So let me just zoom onto this diagram and let us see. Uh, Wait a minute, I have pressed the wrong button. So here, let us just focus on this diagram for a while. Oh God. Yeah. So let us focus on this diagram for a while, right? So you can see that in mode number 1, we are talking about first of all taking inputs from the peripheral. Outputs will be obviously understood in the similar way, right? So you see here, this is your 8255 IC, and these are some internal connections which are shown here, right? So port A is there, obviously 8 bits of that port will be there, and port B is there, obviously 8 bits of that will be there, and those two will be used to transfer the data. And port C will be involved in the process of handshaking. So internally, you see that P0, the 0 bit, 1 bit, and 2 bit of port C, it will be used for this particular purposes. And similarly for port A, this 3, 4, and 5 bits of this port C will be used. So port C is of 8 bits, and you are using 6 bits for this purpose of handshaking. So the remaining 2 bits, they can be programmed in mode 0. So if a port is programmed in if a port A or port B is programmed in mode 1, still you have 2 bits which remains in this C port. So those bits can be used for simple input output purposes in mode 0, right? But we are not talking about that now. So what happens is, let us understand this handshaking mechanism. So let's see port A only. The same logic will be applicable to this port B also. Suppose that a device is connected to it, and the microprocessor which is connected prior to this has requested to read that device, right? So what will happen is, we are uh, trying to understand this from the process of interrupts, right? Microprocessor hasn't requested anything. I'm sorry about that. That's a wrong statement. Suppose this externally interfaced peripheral, which is connected at port A, has got some data to transfer, right? So it will do is, it will first of all put this strobe signal, STB signal, STB bar signal for port A, as it will activate it, right? So it's an input signal. You can notice it from this arrow. So it will put this strobe signal on, and it will also put the data into this port A, right? So this 8255 PPI will know that the externally interfaced peripheral has transferred some data, and the data is already available onto port A. Now, having received that data, this 8255 is a very gentleman kind of IC. It will acknowledge that through IBF, input buffer full. That is, okay peripheral, I have received your data, and my input buffer for this port A is full. It has received some data, so this input buffer is full, right? And inside this 8255, for we saw this group A control. So this INTEA that you see here, it is from group A control only. So this is for interrupt initiated handshaking process. So if this bit is 1, this is just one flip flop. If this bit is 1, then it will take the ending of this strobe signal and this IBF signal and this INTEA signal. That means interrupts are enabled for 8255 device. This indicates this thing. So if all of these three things are 1, then it will, through this third bit of port number C, it will generate an interrupt signal, and this interrupt signal will be sent to the microprocessor, right? Because to begin with, to begin with, the externally interfaced peripheral which was at port A, it wishes to transfer some data, so it has given that data to port A. Then through this process, it has acknowledged 8255 has acknowledged that I have your data. Then now, 8255 will transfer this data which is available at port A to the microprocessor. For this, it has generated one interrupt. It will interrupt the microprocessor, and there will be an interrupt service routine inside microprocessor. We have seen how to write them, and that interrupt service routine will take that data. So once this happens, uh, this process is over. The process of transfer of data from peripheral to the microprocessor is over. Now what do we need to do? Once the data has been transferred, the some signals, they need to be adjusted, right? I mean, you cannot put this strobe signal and IBF signal and INTR a signal on in that case. So we will discuss that when we will discuss this timing diagram, right? So first of all, the transfer of data is complete. The same logic is applicable to this port B also, right? The same logic is applicable to port B also. And you can see that for port C, 6 and 7 bits are free, so they can be used in any input output mode, right? Now, the thing is, let us also have a look at how this 8255 is connected to this particular external devices. So you can see that at port A, and this is port B. They have written port A here, but this is port B. So some input output device is connected here, and it has connected its 8-bit data to this port A and port B, and this strobe signal is there. Then this IBF, input buffer signal, is there from the 8255 to this peripheral, and same logic is applicable here. And this interrupt for this A port and interrupt for B port is also available here. So this is how we operate in mode 1, and in mode 1 we are using the mechanism of interrupts. So that's what we have seen here. Now let us come to the timing diagram of this complete situation. So this is the timing diagram for the situation that we have discussed. First of all, what will happen is, the first thing that happened in our discussion was the peripheral wishes to transfer some data, right? Peripheral wishes to transfer some data. So it will just we have seen that this strobe signal will be made on there, right? So you can see that the first signal that goes on is this strobe signal. So strobe signal is on. Strobe signal is on here, right? Strobe signal is on, and the data is, put onto the peripheral. Data is put from the peripheral to the 8255 IC. So that's what has happened here, and this has triggered this arrow that you see. This arrow has triggered this IBR. Sorry, this is IBF. This is not F. This is not R. This is F. Input buffer full. So this has triggered this input buffer full signal. I mean, this strobe signal was there from the externally interfaced peripheral, and the data was made available on port A, right? And after this has been received by 8255, the action of these two has triggered this input buffer full IBF signal. So this has been opened, right? Then, since this has been opened, an interrupt has been generated. An interrupt has been generated for this port number A that we have discussed. So interrupt has been generated. After the interrupt has been generated, the microprocessor's subroutine will see that it has to read the data because an interrupt has been generated by that device. So this read signal will be activated. So this is active low signal. So we have made a value 0 here. So this has been activated, and the data has been transferred from 8255 to 8085 or whatever processor you are using. So this is the complete thing depicted in terms of timing diagrams. It's not very tough to draw this timing diagram, because if you remember the sequence of events, this is very easy, right? So this is what happens for this transfer of data in mode 1. So there is this acknowledgement strategy, which is implemented by this input buffer full IBF signal here. So this acknowledgement strategy is already there. So this is interrupt driven mechanism. However, it can also be done, the input can also be taken without using this interrupt mechanism. How it can be done? The second way is status driven. The second way is status driven. So in this status driven mechanism, what happens is there is a polling mechanism. What is called as what is polling? Let us discuss it. In the first mechanism, which was interrupt driven, when the externally interfaced peripheral was trying to transfer some data to the microprocessor, it has given its data to 8255. 8255 being a gentleman, it has acknowledged it to the peripheral, and it has interrupted the microprocessor. So microprocessor, whatever work it was doing, it was busy. It has interrupted this microprocessor. So microprocessor took the data from this port A and resumed its work. So this is one way. In status driven method, this interrupt mechanism will not work. In that method, this flag will have a value of 0. This INT flag or B flag that we have selected, it will have a value of 0. So this interrupt signal will not be generated, but microprocessor, through its internal mechanism, it will continuously check the status of these ports A and port B by seeing the control word register format, right? So this control word register format is there, and it will check this format. And it will take the data from the peripheral. So the microprocessor will be busy now in dealing with the peripheral, because it has to continuously check that peripheral whether it is trying to give some data or not. So this is not a very efficient way of doing that. So status driven mechanism is not preferred, because we want microprocessor to be as free as possible. This is the format of the control word. You can see here IBFA, that is input buffer full. INTEA is also there. It will always be 0 for status driven thing, and if it is not status driven, it will be 1 for interrupt 1. But for status driven, it has to be 0. So microprocessor, through its internal program which some user has written, it will continuously check this register at periodic intervals. So that will give some additional tasks to microprocessor. So we don't want that. So this interrupt driven mode is preferred there. So status driven mode is also called as polling mode, right? So now let us have a look at some features of mode 1. In this mode 1, what happens is two 8-bit ports A and B function as input output ports. That's what we have already seen. We have seen the mechanism for input. For output, we are going to discuss it shortly. Each port uses 3 lines from port C as handshake signals. So this is what we have also seen here. So 3 lines, 2 for input and 1 for output, has been used as handshake signals. The remaining 3 lines of port C can be used as simple input output. That means in mode 0, right? The input and the output data are latched, obviously. Then port C handshake signals can be used to interrupt the CPU. That is, the interrupt logic is supported by 8255 to transfer the data from 8255 to CPU. So these are some important points of mode 1. Now, let us come to the output portion. I mean, here we have learned how input is taken. This is the exact same thing, but this is for output. Here we have input buffer full, strobe signal, and interrupt signal. Instead of that, when this 8255 wants to send some data, you don't have input buffer full. You will have output buffer full, OBF, right? And in this case, input case, this acknowledgement was given by 8255 to PPI. Here the reverse will happen. Sorry, 8255 to externally interfaced device. Now here it will be given by this externally interface device to this 8255. So it is ACK or acknowledgement, right? Then there is this interrupt signal also. And similarly, inside this inside this 8255 PPI, if you will see the structure, different number of bits are used. 3 bits are used, but their number is different from the input bits. So the format is different, but the mechanism will remain essentially same. And the status, for status driven thing, that is polling thing, we have this particular format here for this control word register, right? So this is fairly simple. On this similar analogy, you can understand it, but I hope you have got the logic behind that. So you can see some more details about this in your textbooks. Now, coming to the mode number 2, which is a strobed bidirectional input output. Strobed bidirectional input output is nothing but it is mode 1 only, but any port can act as, I mean, only port, it is applicable to port A, and that port can act as both input and as both output port. Now, in mode 1, one important point to note was, for example, if you see this, PC4, PC5, and PC3 are used for port A for input mode. And if you see the same thing for the output, PC6, 7, and PC3, they are used for output. So the bits are different. So the same port cannot act as input and output, right? So to overcome this problem, they came up with this mode number 2, which is called a strobed bidirectional input output. And in this only, port A will be transferring the data in bidirectional mode. So here you can see that the interrupt signal that we were generating earlier, it is not generated directly. It is further coupled with the interrupt signal that we are receiving from this output one. So this is for input and that is for output. And that's how you generate a single interrupt signal, right? So I mean, for this is the OR gate. So whether you are taking input or you are taking output, if it is one, the microprocessor will be interrupted through this INTR A signal. So rest detail, they remain the same. Only this change is there, right? This change is there. So apart from that, you can easily understand that if there is 8255 PPI and in this externally interfaced peripheral, then this port A, that is 8 bits of that will be converted, it will be connected to this peripheral, and according to this diagram, appropriate connections will be made for output buffer full, acknowledgement, strobe, and input buffer full. And this interrupt will be only a single pin because you can see that it has been connected here. So the explanation for this also remains very similar, and it has also got this status driven mode for which the format is given there, right? So it is now easy to understand this timing diagram also. I leave this as an exercise for you to understand. If there are any doubts, you can always ask me. So I think this is it for this 8255 PPI. And as I told you that it's a device which is having several layers of operations. So quickly let me walk you through what we have done in today's lecture. So we have started with this 8255 spin diagram. We have understood it has got port A, port B, and port C. Port C can be used in nibble format. Control word register is also there, because of which this device is programmable. After that, we have seen the functional diagram. So with every group means port plus some portion of C port, right? Port A is there and upper portion of port C is there in group A, and port B is there and lower portion of port C is there in group B. So this way we have seen the functional diagram also. Then we saw there are two modes, bit set reset mode, which was very simple mode, which was only used for C port. So to be able to set or reset some of the bits B1, B2, B3 of port C, you have to use this particular mode. Now you can understand the usage of this mode better, right? So suppose you want to set or reset the interrupt flags. You want to set or reset the interrupt flags, then for this port A you have to use D4 bit, and for port B you have to use this D2 bit, right? And apart from that, if you want to set or reset any bit, then you can use this particular format, right? Then we have discussed that there are two modes, BSR mode and IO mode. So BSR mode is done here. Then for IO mode, we saw that there were three cases. There were three cases, that is mode 0, mode 1, and mode 2. Mode 0 is simple data transfer without reliability. Mode 1 and mode 2, they have some handshaking mechanism by which the data is transferred more reliably and the microprocessor is more free, right? So then we discuss this mode number 0, which is very simple data transfer mode, and microprocessor has to take care of the fact that it transfers its data at a speed which is lower than the speed of acceptance of this externally interfaced peripheral. Then in mode 1, we saw that handshaking mechanism is implemented. So we saw the appropriate diagrams. And mode 2 was bidirectional strobed. And bidirectional means that this port A will only be functioning and it can transfer the data. I mean, it can take or give the data to the port. It can change its role. But in mode 1, if some port is decided as input port, it has to remain as input port. If some port is decided as output port, it has to remain as output port throughout the operation. However, in this strobed bidirectional mode, this nature of this port can be changed in runtime also. So that's what we have learned about this 8255 programmable peripheral interface. We will practice some small programs of 8255 PPI also. They're very simple in nature. So I guess this is more or less than it for this particular lecture, and I will see you in the next video. Thank you very much for watching this.